Hello, today's video is on section 6.2. We're going to talk about something called integral notation. An integral is going to be a huge part of calculus. We spent the first half of calculus taking what are called derivatives. We know a lot about derivatives now. The whole second half of calculus is going to focus on integrals and what they are. So here's where we're going to start off right away. We learned this a little bit ago. LRAM, RRAM, and MRAM are great approximations for area under a curve. If we want that approximation to be more accurate, we just use more rectangles, right? If we want exact area, however, we got to use a whole lot of rectangles. In fact, we got to use an infinite number of rectangles. So the integral notation is actually a notation that finds the exact area under a curve, and it uses an infinite number of rectangles. So basically the integral notation is finding the limit of the total number of rectangles that we added up. Just like we found the limit notation of derivatives, this integral thing comes from that same idea. So not surprisingly, we can use calculus to find the limit of those infinite rectangles. It's used so often, it's given its own notation, and it's called an integral. So we're going to talk about that notation today. Here is what the integral notation means. So there's a few things that are, few parts about it. So there's the integral sign. So that's the integral sign. So if you ever see that sign, you know we're talking about area. This is the lower limit and the upper limit of integration. So that tells us where to start our area and where to stop our area. That would be like this one would start at 0 and end at 4, right? So that would be the start and stop of my integral, finding the area. F of x, that's just your function. And there's always going to be like a dx there. That's the variable we're integrating with respect to. We've talked about that when we're taking derivatives, like the derivative with respect to x, the derivative with respect to y. Same thing for integrals. This would be the integral with respect to x. We're definitely going to focus on just dx there right now. Eventually, we'll talk about finding integrals with different variables besides x. All right. A couple things about where this comes from. It's, as we had mentioned, it is the sum of an infinite number of rectangles. That's why this integral notation kind of looks like a stylized S. It's because it literally stands for the sum of a bunch of rectangles. How do you find how do you find the area of a rectangle? Well, you take the base times the height. F of x would be the height of your rectangle. If I had some function, right, where that's my f of x, and I drew a bunch of rectangles there, the height of each of those rectangles would be f of x, right? That's this line right here. So that's the height of all the rectangles. So that's my height. Times the width of each of those rectangles would just be a small change in x. That's that dx. That'd be the width of the rectangle. We use dx because dx again stands for an infinitely small change in x. And since we're talking about an infinite number of rectangles, that dx, that width of each rectangle, is going to be infinitely small. So f of x is the height of each rectangle, dx is the width of each rectangle, width times height, that's the area of a rectangle. And then I just sum them all up. So that's where these parts of that integral came from. We'll talk about finding integrals using calculus in a couple other classes. It's actually pretty easy. It's not hard at all. But for today, we're just going to focus on the fact that this notation, that integral notation, means we're looking for the area under a curve. So integral from a to b of f of x dx is equal to the area under the curve f of x from a to b. So if this was my curve f of x, this area right there, that's equal to this symbol. So that's saying, hey, you want to know that area? That's this thing. That's the integral from a to b. All right, couple of points about it. If the curve dips below the x-axis, the value of your integral is going to be negative. Now, I'm using this quotation mark. I got to be careful here. There isn't such thing as negative area, right? That'd be like negative volume. It's not really a concept, but you could think of these like positive areas, and you can think of that section right there like a negative area, because the value of the integral over here and the value of the integral over there is going to be a positive value. The value of the integral here is going to be a negative value. It looks the way that it looks by the way I'm looking at this. If I were to guess the integral from a to b of this f of x dx, I would say that total area of that total integral would probably be 0, because it looks like the positive values here and here are about the same amount of area as that negative value, so they'd cancel each other out. So that total net change would be 0. Again, there isn't really such thing as a positive area or a negative area. It's just any amount of area here. When you take the integral of that, the number you're going to get out would be a positive number. Any integral, any area here, when you take the area of that part, you're going to get a negative number. We'll talk about why it makes sense here. So why integral values above the x-axis are positive and below the x-axis are negative. Here's why. When I find f of x dx, right? These are my dx, it's a change in my dx. When I find these heights, when f of x is above the x-axis, those are positive values, right? This is like a value of, let's say, 3, and then 4, and then 5. Those are all positive values. 3, 4, 5. Those are, right? If I did some base times 3, that's going to be 3. Some base times 4, that's going to be 4. Down here, though, those values of f of x are negative. That'd be like, let's say, -1, -2, -3. When I take something like, let's say that's 0.00001, it's supposed to be really small, right? If I take that times -1, I'm going to get a negative value. So anything down here results in a negative integral. Anything up here results in a positive integral. Another way to think about that, and again, why it should make sense like that, is let's actually assign some values to this curve. Let's say that that curve is measuring velocity. What does it mean when I've got a positive velocity? Well, a positive velocity means I'm moving forward. So those are all positive values. So that would be when I'm moving forward. How am I moving past this time though? Well, that's got a negative velocity. Velocity can be negative. So negative velocity means I'm moving backwards. So if I moved forward for a bunch of time, and then I moved backward for a bunch of time, that I might end up starting in the same spot I ended up. Like, let's say I move backward, that's fine. Say we found this area. And since we're taking feet per second times seconds, when I find that area, feet per second times seconds, those units cancel out. I'll have an answer in feet. Let's say this quote unquote area ends up being 20 feet. That means over this time, from time 0 to time, let's call this 8 seconds. Over those 8 seconds, I moved 20 feet forward, right? Well, let's say we did this area and we found that that total distance was -10. That means I went 10 feet backwards. Let's say this ended at 12 seconds. Well, if I went 20 feet forward and 10 feet backward, that means the end result was I ended up 10 feet forward, right? 20 feet forward, 10 feet backward. That's why areas under the curve can be thought of as negative areas. Yes, area can't be negative, but the integrals can. So the value of the integral from here. Actually, this will be really good. So I'm going to actually change that. Instead of -10, let's call that -9 feet. All right, so to check your understanding of integral notation, let's just do 3 quick integrals. Let's do the integral from 0 to 8 of f of x dx, the integral from 8 to 12 of f of x dx, and the integral from 0 to 12 of f of x dx. See if you can find the value of those 3 integrals. Maybe pause the video. All right. Integral value from 0 to 8. Well, that's all the area under here, which is a positive value. We said that was 20. So that's equal to 20. The integral from 8 to 12. Well, that's all of this movement. We change that to -9. So that would be a value of -9. If I said from 0 to 12, well, that's all of this put together, all of that 20 plus that -9, that would be 11. Since this particular function is measuring velocity over time, we already found out that these values actually have a unit. That would be 20 feet, which means you moved 20 feet forward. This would be -9 feet, which means you moved 9 feet backward. That would be 11 feet, which means the net result was a net movement of 11 feet forward. All right, let's actually do a few problems. So here's what the problems you're going to see today. We don't know how to find integrals yet, but there's still some work that we can do. So for instance, if I told you that the value of this integral, sine of x dx, from 0 to pi, if I told you that that value was 2, you should be able to use your knowledge of sine to come up with these integrals. It might be a good idea to try to pause the video and see if you can do them on your own. All right, the integral from pi to 2 pi. Well, that's from here to there. It's going to be this section, which looks like it's going to be the exact same area as this section here. It's just now under the curve. So instead of if this one here was a value of 2, that one under the curve would be a value of -2. Second one, integral from 0 to 2 pi. Well, that's all of this starting at 0, going all of that there and all of that there. Well, if the first half was 2, the second half was -2, 2 plus -2, they're going to counteract each other. That integral is going to be equal to 0. Last one is very similar. Last one is asking us to find the integral of sine of x from -pi to pi. Well, that's starting here at -pi, ending there at pi. So it's going to be all of this, which is -2, and all of that, which is 2. Adding those together, net result of 0. All right, let's try another one. Same thing. Integral from 0 to pi of sine of x dx is 2. These ones are a little trickier. See if you can figure these ones out. All right, the first one shouldn't be too bad. From 0 to pi over 2. Well, that's just halfway. So if I just did halfway, half of that area, that's going to be 1, since the whole area is 2. Easy enough. This one requires a little bit more knowledge. What happens to sine of x when I multiply it by 5? Well, when I multiply sine of x by 5, let's do a quick sketch here. When I multiply sine of x by 5, it's still got that same curve. But instead of going up to 1 and down to -1, it's going to be stretched by 5. It's going to go up to 5 and down to -5. So if I want the integral from 0 to pi of that, well, that's the same function, but stretched 5 times bigger. So since every rectangle there is 5 times taller, the total area is going to be 5 times more area. 5 times 2 is 10. This last one's probably the trickiest one. What happens when we add 5 to sine of x? Well, adding 5 to sine of x doesn't stretch it by 5. It moves it up 1, 2, 3, 4, 5 units. So it's still sine of x going up 1 and down 1, but it's moved up 5 units. Right at, that's y equals 5. So if I want the integral from -pi to pi, well, -pi happens right here. Pi happens right there. And to see what this is equal to, let's actually look at this. That area in pink is pretty easy to find out. It's got a base of 2 pi, a height of pi. That whole area there is 10 pi. But that's not really the area I want. The area I want to have only goes up to here, but then it goes all the way up to there. Thing is, that area is 2, so I just have 2 extra there. That area that should be missing right there is also 2, but it's a -2. So this section right here and this section right here kind of balance each other out, right? I've got 2 units too many on the right and 2 units too few on the left. So it turns out that the area overall is the exact same as the area of this pink rectangle. And the area of that pink rectangle is 10 pi. All right, that was a tough one. So we don't know how to find integrals using calculus yet. We've already mentioned that, but we can still find some other integrals on our own. The ones you're going to be asked to do in your homework are more like this. So it says, hey, find the integral from 0 to 3 of 2x dx. We can do that. We know it's just the area under your curve. So here's the curve of y equals 2x. It's the area under the curve starting at 0 and ending at 1, 2, 3. So all this is asking is, what is the area right there? Well, that's not so bad. That's a triangle. What's the base of that triangle? Base of that triangle is 3. What's the height of the triangle? Well, the equation is y equals 2x. So when I plug a 3 in, I should end up here at 2 times 3 is 6. That's a height of 6. So the area of that triangle, area of a triangle is 1/2 base times height. In this case, 1/2 times a base of 3 and a height of 6. That's equal to 9. Let's try just a couple more. Same thing, y equals 2x, but now I want the area or the integral from -1 to 2. So I'm going to start at -1 and end at 2. So that means I'm starting here at -1 and ending there at 2. Well, again, we've got some part of this from the curve to the x-axis there. That's going to be a negative value because it's under the x-axis. From the x-axis to the curve here, that's above the axis, that'll be a positive value. So let's just find the area of each of those triangles separately. This triangle, again, it's a triangle, so area equals 1/2 base times height. It'd be 1/2 a base of -1, or sorry, no, a base of 1, because it's a height length of 1. And you can think of this height as a negative value if you like, or you can just think of it as a positive value and then switch it. I like think of it a negative value because if the equation is 2x, if I put a -1 in for my x, -1 times 2 is -2. I do consider this a positive one instead of a -1. The reason why is I'm starting here, and if I move from here, let's do this. If I move from here to there, to there, to there, that's always a positive movement. But if I move from here down to there, that's a negative movement versus moving from here to there, that's a positive movement. I am starting at -1 and moving positive to 0. That's a movement of 1 versus starting at 0 and going down. So this is a 1 there and a -2 there. Again, you could just find the area of a triangle, say it's got a length base of 1 and a height of 2, that's fine. And just know that since it's below the x-axis, it's negative. That's another way to do it. I'm going to write it as 1 times -2, which is just -1. Regardless, I know the value of that should be negative. So if I somehow get a positive value out, I'll know I did something wrong. It should be a negative. All right. Area of this triangle. It's also a triangle, so 1/2 base times height. This will be 1/2 times, this is a base of 2. If I plug a 2 into my 2x, 2 times 2 is 4, that's a height of 4. 1/2 times 2 times 4, that's 4. So if I combine those together, the total value of the integral is 3. All right. This one you can do on your own. I'm just going to talk about it a little bit because I feel this video is getting long. if I wanted to go from -2 to 2, I'm looking for this area. So there are a number of ways you could find that area. One way you could find it is by using the fact that that is a trapezoid. And you could use the area formula of a trapezoid. Area of a trapezoid is 1/2 times the height times base 1 plus base 2. Definitely works just fine. If you didn't want to use a trapezoid, you could use a couple of triangles. I could say, hey, I can take this large triangle right there, and I could take off this orange triangle right there. And if I find the area of the pink triangle and subtract off the area of the orange triangle, I'll be left with just this area right here, which is what I'm looking for. So you could use a couple of triangles, you could use a trapezoid formula, whichever you like. Again, I don't think I'm going to do that. Maybe I'll do it quickly for your notes, probably in both ways, but I'm not going to do it in the video because I think the video is getting long. I think you get the idea. All right, last one. If I asked for this integral, that integral looks crazy complicated, but here's the graph. I'm looking for the area between the x-axis and x-axis and the curve from -5 to 5. Hopefully you can recognize that shape. That is a half circle. It's a half circle underneath the x-axis. Area of a half circle is 1/2 pi r squared. This circle has a radius of 5, so the area of that is going to be 1/2 pi times 5 squared, which is 12.5 pi. But of course, this half circle is below the x-axis, so the value of this integral isn't going to be a positive value, it's going to be a negative value. So my answer is negative 12.5 pi. All right, your assignment is 6.2, problems 7 through 27 odd. Give them a shot. As always, I'm here during my office hour if you have questions. Take care.